Hi, this is Sheridan, and this is Analog Circuitry 101. This is our second video. We will be covering capacitors in this video. So capacitors are pretty simple. They're just two metal plates that are separated by an insulator. And what's special about that is a capacitor works with electric fields. So when you generate an electric field on one of the plates, it causes a reaction in the other plate. Let me try to explain that a little better. So here's a animated GIF that was supposed to be animated. There it goes. So inside a capacitor, what happens is one side gets charged with electrons, and as that plate charges up, it pushes electrons out of the other plate without actually transferring current across the plate, because it builds up an electric field that pushes pushes like charged particles out of the other plate. However, the more a capacitor gets charged, the harder it is to push current into this top plate. Let me demonstrate that. So right now this is our capacitor circuit, and we have our capacitor. This is our charging path, and this is our discharging path. So right now we have the capacitor fully charged, 5 volts, which is the same as our power supply. And if I flip the switch, I can make the capacitor discharge in this particular curve. And the math behind this curve is determined by multiplying our resistance times our capacitance. So capacitor it both charges and discharges in a specific amount of time, which makes the capacitor very useful for making circuits that oscillate at a specific frequency, or filtering frequencies, or detecting frequencies. So whenever you have a time-sensitive circuit, a capacitor will pretty much always be used in some way. So in this circuit, we have 20 microfarad capacitor with a 1K resistor. Let's bring up our calculator here. So our time constant will be 0.00002 for 20 microfarads times 1000. And that is 20 milliseconds. So one t period of this discharge curve is 20 milliseconds, and 5 is the full time it takes to discharge. And no matter what your setup is here, no matter what inputs you give it, it always takes 5 time constants to discharge. So if we change this to, let's say, 500 ohms, and we charge it and discharge it. Okay. We can see that since we decreased our resistance, we've also decreased our time constant. So if you look at these two discharge curves, you will see that the second one is a lot shorter than the first one. So we can increase our capacitance Now when we increase our capacitance, it will take longer because there is more of a plate to fill, so to speak. Let's see. Run. Okay. So now you can see that our charging time is now a lot longer because there is a bigger capacitor to charge. The other handy thing about capacitors when charging and discharging is that you can actually pause the charge time by breaking the circuit. As long as there is no discharge or charging path, a capacitor will hold the charge that it was holding when the circuit was broken. So let's demonstrate that. So we fully charged our capacitor. We're going to switch to discharge and break the circuit. So you can see that it started to discharge, but as soon as the circuit was broken, the capacitor stopped discharging, but it held the charge that it had. Why is our... Oh, that's the sag, okay. So we can resume discharge by reconnecting the circuit and pause it anywhere we want. Now, of course, in real life, a capacitor will not hold its charge forever, but you can get it to hold its charge for a pretty long time. In microwaves, there's a capacitor that's used to filter out AC so the magnetron gets DC circuitry, and there is actually a resistor that's built into the capacitor like this, so the capacitor will not hold 4,000 volts forever. But we aren't working with high voltage here, so we don't need that. So I'm going to charge the capacitor again. And this time I am going to add this LED diode to the circuit. So we can force the discharge we can force the discharging of the capacitor to go through certain components, like this LED diode, and I guess that's kind of redundant. And we can see that we can run the LED for a short amount of time, but eventually the capacitor runs out of charge. And the same thing would happen. Let's add an LED on the charging circuit. Well, I'll get to that later. So we can force our discharge through the LED and get it to run for a certain amount of time. But what happens if we put an LED on our charging circuit? Let's see. LED. There we go. And it's actually going to be this way. I'll cover LEDs later, but for now they're just something we can use to tell when a circuit is on. So I'm going to flip this over and start the charging cycle. We see that the LED turns on. However, even though we are charging the capacitor, the LED doesn't stay on forever. But but it has a continuous 5 volts into it. You see, what's happening here is that when the capacitor starts charging up, this yellow line is our current that's being used to charge the capacitor. So it goes down over time because there is more resistance, and the more resistance you put into a circuit, the less current you're going to get out. So we start with low resistance, and then we get high resistance. So what's happening is the capacitor is charging up to make an equivalent resistance enough so that it can't let current through the LED at a certain point anymore. Okay, I don't know why I'm lagging, but I am. Why am I... Okay. Well, Sometimes this happens with Falstad, not very often. It's reset. Usually you can just fix it with a reset. There we go. Running smoothly now. Okay, well that's it for capacitors. Next time I will probably be talking about inductors. Oh, I was going to show you this. So here's a little bit more mathematical explanation of charging and discharging times. So as we can see, it takes 5 time constants to reach full discharge. And you may, I like to think of these as standard deviations, to use a very statistics specific term. Try to say that 5 times fast. Because they do sort of function like standard deviations, because a standard deviation takes up the same amount of space on your x-axis in any bell curve. So voltage and current in a... Oh, yeah. One thing I forgot to mention about capacitors. Voltage and current oppose each other. I don't know how else to put it. The more voltage a capacitor builds up, the well, I guess I sort of did cover this. The more voltage a capacitor builds up, the harder it is to force current through it. So we can see our current decreasing or approaching 0 as the capacitor charges up, while our capacitor approaches maximum voltage, or minimum voltage in this case. And as always, it takes 5 time constants to do that. The time constants are calculated by RC. I think that's it. I will be using capacitors a lot in the future. Like I said, they were very useful. So if you don't quite get it now, you may get it in the future when it's in context. We haven't actually gotten to useful circuits yet, especially in filtering and rectification. So I will see you next time. I close the video.